Discrete probability distributions. These are basically theoretical probability distributions that we are going to discuss today. We are going to discuss mainly three of several probability distributions in the discrete case. These three are the binomial distribution, the Poisson distribution, and the geometric distribution. And when we refer to theoretical probability distributions, what does this mean normally? It means that sometimes we do have certain contexts, and when we look at these contexts, we will basically see that there are certain characteristics of that context that enable us to use one of these distributions. There are certain conditions for which one of these distribution would be applicable. And we are going to have a look at some examples and explain all this today. So we'll start by the binomial distribution. The binomial distribution is an extension of one distribution that we call the Bernoulli distribution. Okay. Now, it is an extension of what we call the Bernoulli distribution. Now, the question is, what is a Bernoulli distribution? In fact, the Bernoulli distribution is the simplest of all distributions that we have. It's the simplest probability distribution that we may have. In what way is it simple? It's because we are considering only two possible outcomes. If we consider, for example, the case of tossing a coin. If you toss a coin, then there are only two possible outcomes that x can take. X can take only two possible outcomes, where x could be either equal to 0 or x could be equal to 1, depending on how you define x. If x refers to head, then the number of head or head, basically here, x is equal to 1, which means if x is referring to if x is equal to head, then x equal to 1. And in other words, x equal to 0 represents a tail. There are only two possible outcomes. The case of tossing a coin can be said to be, we refer to as a random variable x to follow a certain Bernoulli distribution. We do write this like that, okay? You see that it follows a Bernoulli distribution where you have a certain parameter that we call P. Now, when you are seeing that for the first time, for some of you, you might ask yourself, what is all this about? First of all, we are generally giving, we are stating here by writing this statement here, we are stating that our distribution x, our random variable x, the random variable x, which is the case of the number of heads obtained, like in this context, either 1 or 0, if we have only one coin. So x can follow a Bernoulli distribution. That's what we say. X follows a Bernoulli distribution with a parameter P. We will always have a certain probability distribution, that is the name of a theoretical probability distribution, with that of a parameter. Okay, with that of a parameter. And in this context, the parameter is P. And what is this P? We will see this P very often, even in the case of a binomial, when I'm going to talk about it in a moment. In the case of a binomial, you will see that P coming in. And P usually is used to represent a probability. And what probability? It is used to represent a probability of a success. Like for us, if we talk about the case of tossing a coin, then obviously the probability of getting the head, if x is representing head, would be basically 0.5, and you say that x follows a Bernoulli with parameter 0.5, as simple as that. So this is the most simplest distribution that we do have, but I'm not going to get into the detail of the Bernoulli distribution right now. I'm just mentioning it for you to get an idea of where the binomial comes from. So the Bernoulli distribution is a distribution that is used generally to refer to only one trial of a certain experiment where you have two possible outcomes, either a success, as you saw, we use the word probability of success, or a failure. If we do not have a success, we will have a failure. So this is what the Bernoulli distribution is referring to. Right? We have a case like in the example of a tossing of a coin where you have only two possible outcomes, either a head or a failure. It depends on the question on what is being defined as a head here. Sorry, on what is being defined as a success. For our example, we are referring to a head as success, so x is going to be equal to 1. So this is what the Bernoulli is about. When you hear this word Bernoulli trials, that's what I'm referring to, is that I'm saying that we are referring to a trial where you have two possible outcomes. Two possible outcomes. That's the idea of what I mean by a Bernoulli distribution. Now, what's the difference between a Bernoulli and a binomial? The difference is very simple. In a Bernoulli, we are talking about the case of tossing a coin. Right? We have only one um, time that this experiment has been carried out. But in the case of a binomial, we will see that this is an extension of the Bernoulli distribution that we have been discussing. It's an extension where we are dealing with not one coins, not one trials, but several trials. It may be, for example, the case of tossing two coins. When you are referring to the case of tossing two coins more than one, then you don't need to work with the Bernoulli anymore, but you work with an extension of the Bernoulli distribution, which is the binomial distribution. Now we can get into the binomial distribution to understand a little bit what the binomial means. Normally, I will explain that through the case of an example here. We'll take the same example that we used to work with earlier for consistency and to make things easier for you to understand. If we talk about the case of tossing three coins, one of the questions that I might be interested in, if I define x as the number of heads, we all know that the probability that x is equal to, let's suppose 2 is equal to 3 out of 8. We already know that. We know that probability that x equal to 1 is 3 out of 8. Probability x equal to 0 is 1 out of 8. And probability x is equal to 3 is equal to 1 out of 8. If you forgot how we got this, please refer to the previous lecture notes on probability where we refer to these different examples. Okay. Now, we just saw that it is equal to 3 out of 8. Very simple. But we will try to look at the same thing differently today. We are going to look at it in a way that, based on the context that we have, can we have a certain distribution that enable us to find this probability in a straightforward manner? Or can we have a distribution that enable us to find the mean of that distribution of x in a straightforward manner, or the variance of that distribution in a straightforward manner, rather than going and doing expected value of x equal to 0 times 1 upon 8 plus, as we did last time, 3 times 1 upon 8. Instead of doing that, do we have a straightforward way of getting all this information? This is where, as I explained to you, we have what we call a theoretical probability distribution. A theoretical probability distribution can be used to get things more easily. The question is, what theoretical probability distribution would be appropriate to model the number of heads if you toss three coins? Which probability distribution would be appropriate to model the number of heads if you toss three coins? As I mentioned to you earlier, there are so many probability distributions that exist. We have the binomial, we have the Bernoulli, you have the Poisson, you have the geometric, you have another one that we call the negative binomial as well. So there are so many probability distributions that exist, but we need to figure out if ever this context, that is the context of tossing three coins and working with a number of heads, we could use one of these distributions to do that. And how shall we know that? How shall we know if ever there is a particular distribution that we can use to do that? And this is where we need to understand what are the conditions that exist to apply these different distributions. We'll start by the binomial. We will have a look at the characteristic of a binomial distribution so that we can understand what so that we can understand whether this case of tossing three coins with when you are looking for a certain number of heads out of it is appropriate for the binomial or not. So how shall we know that? Let's have a look at the different conditions. Let's take the example of tossing three coins. If you toss three coins and you are referring to x as a number of heads, yeah? If you toss three coins and you're referring to x as the number of heads obtained from tossing these three coins, we need to understand that there are certain characteristics of this experiment. And these characteristics, are they similar to the case of binomial, or are they similar to the Bernoulli? The first thing that you would understand is that we are tossing three coins. The Bernoulli, for example, is not appropriate based on what I just explained earlier. The Bernoulli is when you're talking about only one trial of a certain experiment, one coin. So it's not appropriate to use a Bernoulli distribution, obviously. So what is happening here? The first thing is that you are referring to a case where you have three identical trials. You are referring to a case where you have three identical trials. That is, you are tossing a coin one time, you are tossing a coin a second time and a third time, but it's the same coin, like it's the same information that you will get from the coin as well. So you have three identical trials. It's important that you note all these information because you will see then how all this relate to what we are doing here in the context of a binomial distribution. All right. The second thing is that when you are tossing a coin, let's talk about one coin. You will see that for one of these trials, there are two possible outcomes that you will have. You will have a head and or you will have a tail. In this case, like we are tossing three coins, we have two possible outcomes. Either you have a head or a tail for each trial. For each trial, you will have only two possible outcomes. Okay. The next thing is that if you consider the probability of a head, if you consider the probability of a head, you will see that it is going to be equal to half for the first trial. It's going to be still half for a second trial, and it's still going to be half for a third trial. So which means that the probability of obtaining a head or the probability of obtaining a tail as well is not going to change. It's a constant thing. It's a constant thing. It doesn't change. So the probability of obtaining a head will stay the same from trial to trial. So these are certain information that you are seeing for the time being. We have two possible outcomes. We have the probability of a head is the same from trial to trial. And there is something else that you would note is that we will automatically assume that each trial that we have, each trial is independent. If you're tossing a coin the first time, if you get a head, then if you toss a coin the second time, it has nothing to do with what happened in the first one. The second trial has nothing, does not depend on what just happened before. It could still be a tail, or it could still be head with the same probability as it was before. So, in other words, it is not going to depend on what happened before. So, which means that the trials are independent. Each trial is independent. The trials are independent, as simple as that. So, the trials are independent. All right. So, we have seen three characteristics of that experiment here. The first thing is that you will see that we are referring to a fixed number of trials. The second thing is that you are referring to a dichotomous outcome where you have two possible outcomes for each of these trials. The next one is that you have a probability of obtaining the head as constant. It doesn't change from trial to trial. And another characteristic that we just saw is that these trials are assumed to be independent. This is how you will evaluate whether a binomial distribution would be appropriate or not. How would I know that? Because we need to have a look at what a binomial distribution, what are the conditions that needs to be satisfied for a binomial distribution to be applied. If these conditions are satisfied through the characteristic of this experiment, then it's okay. We can say that the binomial distribution is appropriate in this context. So let's have a look at the conditions, and then we will get to this slide where we are going to refer to this formula that you see there. All right, we'll get to this formula in a moment. So let's get to the conditions of the binomial distribution. What are the conditions that need to be satisfied for the binomial distribution to be applied? The first condition is that the binomial distribution, to apply the binomial distribution, the trials should be independent. The trial should be independent. Is this condition satisfied in our example here? Let's make a sort of checklist. We obviously understand that these trials are independent because this is an assumption that we are making. If, by the way, these trials were not independent, then the probability of head would have changed from trial to trial. But we just say that the binomial, we just say that the probability is going to be fixed from trial to trial. The probability of head doesn't change on the second trial, it doesn't change on the third trial. So automatically these trials are independent. These two are kind of connected if you look at this. All right. So then the first condition is satisfied. So we say that, okay, for a case of tossing three coins where you are looking at a certain number of heads, the first condition is that the trials are independent is being satisfied. The second condition for us to apply the binomial distribution, hence the word by the way, binomial means we are referring to two possible outcomes. All right. We also have another distribution that we call the multinomial distributions, where the multinomial distribution does not refer to two possible outcomes, but more than two. But here we are referring to the binomial, means two possible outcomes. So each trial results in only two possible outcomes labeled as a success or a failure. Now you will note that here we are using a general term to describe the binomial distribution because it depends on the question, it depends on the context. Here we are talking about coin, we are referring to the probability of head or probability of tail. We are referring to probability of head or a probability of tail, which for us, we are referring to x as a number of heads. So the success for us, the success is head. If we refer to x as a number of tails, then for us the success would have been tail. So I repeat, x for us represent the number of heads. So for us the success represent head. In other words, the tail represent the failure. So here we are referring to two possible outcomes, a success and a failure. This is the case for us where you have only two possible outcomes, a success and a failure here. So we have only two possible outcomes. So in other words, the second part is satisfied where you have two possible outcomes. Then And the third one is that the probability of success in each trial, which we denote as P, as you saw me writing earlier for the case of the Bernoulli, all right? This P refers to the probability of success, all right? The P, each time you're going to see P in a theoretical probability distribution in this course, the P would be used to refer to the probability of success. Now, what is the probability of success? As I said to you, it depends on what is the success. All right, as what is you define as a success. All right, for our example here, we are defining x. We are defining the success as head. Why we are defining x success as while we are defining head as success because we have defined our random variable as a number of heads. So we are interested in the number of heads, which means the number of heads is the success. So what did we just say here? The probability of success in each trial is constant. Is this the case for our example? The probability of success. What is the probability of success? Success is head. So the probability of head is half. Now, is this probability constant throughout each trial? We just said that earlier. We said that it is equal to half in the first trial, in the second trial, the same thing, third trial, the same thing. It doesn't change. The probability of head will not change from trial to trial. It will be constant. So we just already mentioned that earlier. So each trial, the probability will not change. The probability of head will not change. So what is this probability of head? It is our probability of success P here. And this is fixed. It is not changing. So the third condition in the checklist is being satisfied again for our example of tossing 3 coins. So we put a tick here. All these are being satisfied so far. Let's have a look at the last one, is that we are referring to a fixed number of trials. Now, what is this fixed number of trials? Is it the case for us? We are referring to 3 identical trials. We are not talking about any case except tossing 3 coins. So if we are talking about tossing 3 coins, first of all, you will understand that we are referring to the same experiment of tossing a coin, a second coin, but these are the same thing. They are the same trial. They are identical trials. They are identical trials because we are tossing the same coin again and again. So, but we have a fixed number of times that we are tossing this coin, which is going to be 3 times. So we have 3 times that we are carrying out an identical trial. So here we have a fixed number of trials as we are seeing here. You could have added the word identical trial here. You could add added the word identical. So you are running this experiment a fixed number of time. For our example, it is 3 for the example that we are referring to. So what is happening here is that the fourth point of the checklist is being satisfied. Because all these conditions are satisfied, it means that the binomial distribution is appropriate for this random variable to model this random variable. We say that the binomial distribution is appropriate to model this random variable. All right. So far, that's how you check these different conditions. We have seen that we are dealing with a case of independent trials. We have seen that we have 2 possible outcomes in this example, a success or a failure, where here the success is a head and the failure is a tail. We have seen that the probability is constant each time. We have just seen that the probability is constant, and we have also seen that we are dealing with a fixed number of trials. For us, it is 3 trials, so it is fixed. Now, it's important that you understand this word fixed number of trial. Why? Because if you are going to do something that we call the negative binomial distribution, if you were to do the negative binomial distribution, then you would understand that from the negative binomial distribution, the number of trials are not fixed, but we are not doing it there. This is why I mentioned this word fixed. It's very important because it has a meaning. It means that this number of trials is not changing. identical. And in fact, you refer to it as n, identical trial letter n. P is used to refer to the probability of success. N is used to refer the number of times that this experiment is being carried out. For us, n equal to 3, and for us, p equal to half if you have a look at this case. Having gathered all this information, now we can get back to the binomial distribution. You remember earlier I said that the probability that x equal to 2 is 3 out of 8. So we know that it is 3 out of 8 when we just worked it out experimentally. That is by doing the table as we explained last time when we talked about the random variable. We know that directly. Okay, 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. So this is just from a table. We get this information. This is empirically obtaining this information. Now, this is why I said probability x equal to 3 out of 8. There is no need basically here to apply the binomial distribution because we already know automatically it is 3 out of 8 just by doing this experiment as we did last time. But if ever we were to use a binomial distribution, could we use it first of all to be able to find the probability that x equal to 2? You would see that yes, we could use it because of what I just explained, because all these different conditions are being satisfied. We could use the binomial distribution. Now, if we can use the binomial distribution to find this probability that x equal to 2, how shall we use this? This is where you are going to use this formula. F of x is equal to ncx p power x into 1 minus p power n minus x for x starts from 0 up to n. So we can use this formula to be able to find the probability that x equal to 2. But before we do apply the formula, it's always important, as I did earlier for the Bernoulli, just to describe the Bernoulli, I said that x follows a Bernoulli. If I talk about tossing only one coin, x follows a Bernoulli with the parameter p as success. But for the case of a binomial, it is also important to state what does this random variable follow. The random variable x, we will say, follow a binomial. You can write it down like this with two parameters now. You will see that things changes. It depends on what distribution that you are applying. In the case of a Bernoulli, there was only one thing that is considered. We had only a probability of success. That's all. But in the case of a binomial, we can't have only a probability of success because now we have also a number of trials that we will be considering, a certain number of trials. So in our example that we just took, we would say that x follows a binomial distribution with two parameters, the number of trials, which is 3, and the probability of success, that is the probability of a head, if x was defined as a number of head, is equal to half. So this is how we define the distribution of a random variable. We say that our random variable x, which is the number of heads obtained, follows a binomial distribution with parameters 3 and half. Why is it so? Why is it a binomial? Because of a different conditions being satisfied, and the n and the p is obtained from what we explained here, 3 coins and the probability of head being half the probability of success. So after having defined your random variable, like if you have a question on binomial distribution or Bernoulli, not or whatever distribution you have, binomial, Poisson, etc., it's always good that you define your random variable first. You will say that your random variable follows. You put that tilde here, and then follows a binomial. So follows a binomial distribution. Then when you have done that, you have denoted what x follows. The next step is to start calculating your probability. So the first step is always to state what is the distribution, as I did here. The second step is now to evaluate the probability. Let's suppose I was interested in the probability of obtaining 2 heads. So the probability of obtaining 2 heads, if I said that x follows a binomial based on what I just explained, if I say that x follows a binomial, it means that I can apply this probability distribution to be able to find the probability of x equal to 2. We are going to have a look at that now. So we have n cx. So we said probability that x equal to 2, so we are referring to x as equal to 2. So we have n cx. N is what? 3, as we said. Cx is 2. X is 2 in our example. And then what is happening here is you need to multiply it by p. What is p? We already defined it as half. So multiplied by half power x. X is 2. Here we go. Multiplied by 1 minus p. By the way, sometimes we do refer to this as q, all right, which means the probability of failure. Sometimes instead of writing this long 1 minus p, we do also write q, which represent the probability of failure. So if we have 3 out of 2, we were not 3 out of 2, sorry, but 3 C2 half power 2, and then 1 minus p, which is half again. 1 minus p means 1 minus half, which is q, and then power n minus x. N is what? 3 minus 2. 3 minus 2. And this, when you are going to apply it, you will see that it's going to give you, will see that when you're going to apply this here, you will see that it's going to give you 3 out of 8. You can take your calculator and confirm this information. So 3C2 is 3 times half power 2 times half power 1 is supposed to give you 3 out of 8. You can take your calculator and confirm this information if you want. So this is what, as I just told you here, the binomial distribution becomes appropriate. Now you might ask yourself, but why did we use this binomial when we just could look at this table here? But let me ask you a question now. Let's suppose you toss 10 coins. You toss 10 coins and I ask you what is the probability that x is equal to 4. Do you imagine doing this table starting from 0, 1 up to 10 and evaluate all these probabilities one by one? That would be a total waste of time and it won't make any sense to do this kind of thing. So this is why, for example, if you want to evaluate the probability that x is equal to 4 if you toss 10 coins, you will need to know that the binomial distribution is appropriate for that context. If you did not know the binomial distribution was appropriate to that context, I don't imagine myself going and doing this one by one through the table and then evaluate this thing. In this example of tossing 3 coins, it's straightforward. Whether you apply binomial or not, it doesn't matter. But in the case where you are dealing with 10 coins, for example, you will have no choice except applying the binomial distribution. That's the only way to make things easier. So this is why we need to know this distribution. We need to know this distribution because it makes things far easier for us to evaluate probabilities. How does make things easier? Because if we have a certain context and these characteristics are similar, the context, that is the experiment, the characteristic of this experiment is similar to the conditions that we can use for a binomial distribution, then in other words, we can use the binomial distribution for that particular experiment. So this is why it is important that you recognize whether a binomial distribution is appropriate or not. I just gave you a set of information that you can use to see whether the binomial distribution is appropriate or not through these different conditions. And we just went through all this a few minutes ago. Now, to make things a little bit easier for you now, I'll erase that. You will see that you got the 3 out of 8. So if you want the probability that x is equal to 4 if you toss 10 coins, if you want the probability that x is equal to 4 if you toss 10 coins, in other words, what you just need to do is probability that x equal to 4, which is number of heads. If you toss 10 coins, is 10 C4, and then half power 4, and 1 minus half power 10 minus 4. Okay, 10 minus 4. So then you just get your answer. I don't need to do this table and evaluate all this from scratch to be able to get this solution in a matter of only a few seconds. All right, that's how you deal with the binomial distribution. So, what's our next step then? The next step is to have a look at what are the properties of this binomial distribution. All theoretical distribution, all of them, has a certain property, right? The binomial has a property. You will have all other kinds of distribution, the discrete case, uniform, negative binomial. You will have for example, the Poisson distribution, the geometric distribution, all of them have certain properties which make things easier for us. Like if you remember for this case here, all right? Remember for this case, as I said to you earlier, if you want the expected value of x, you would take 0 times 1 upon 8 plus 1 times 3 upon 8 and so on. And 3 times 1 upon 8, you will get 1.5, for example, but you will have to go through this tedious process of evaluating these probabilities by multiplying them. But the advantage with theoretical probability distribution is that if you want to find the expected value of x, you don't necessarily need to do this step yourself. You don't need to go through these step one by one on your own because there are certain properties which make things easier for you to evaluate these expectations directly. What are these properties? Here we go. The first thing is that the mean of your random variable x, if x is a binomial random variable, like the case of tossing the number of heads obtained, all right, from tossing three coins, then the mean number of heads obtained is defined as np, all right, n times p. So in the case of tossing three coins, do you remember? In the case of tossing three coins where we were working with before, if we were to evaluate it empirically, that is, empirically means based from experiment, we saw that it was 1.5, as we did last week, all right, last time in the previous lecture. So we saw that it was 1.5. Now, if we evaluate it like 0 times 1 upon 8 plus 1 times 3 upon 8 and so on, we'll get 1.5. But imagine how tedious this process is. But if you know that x follows a binomial, like in our case, it follows a binomial, it's just a matter of one line where you take n, which is 3 for us, and you take p, which is half for us, you multiply them, and you see that it is equal to 1.5. You did not have to go through that tedious process of taking 0 times 1 upon 8 plus and so on till the end. No, you didn't have to go through that tedious process because it follows a binomial. We know that the mean is just 1.5 because it is n times p. You see how easy it becomes when you have a binomial distribution. Like in the case of tossing 10 coins, and x is still defined as number of heads. You don't imagine yourself going and doing 0 times whatever value plus 1 times whatever value up to 10 times whatever value. That would not make any sense to do that kind of thing. So because x follows a binomial based on what I explained, then we know that if we want to find the expected value of x when we are tossing 10 coins, this is equal to 10 times half. Again, probability of success is half. So 10 times half, which is 5, we are done. We get the expected number of heads if you were to toss 10 coins. And the same vein, if you want to find the variance, instead of going through that tedious process that we did earlier, 0 times 1 upon 8 plus 1 times 3 upon 8, etc., subtract the mean to the square, we can just apply this here. And if we want to find the variance of x, what we just need to do is to do 10 for the case of tossing three coins. For the case of tossing three coins here, as we did, so the case of tossing three coins, so variance of x is equal to 10 times half times 1 minus half. Right? So it is 0.5 multiplied by 0.5 multiplied by 10. Sorry, I mean 3 here because we were dealing with the case of 3 coins. Excuse me, not 10. The 10 also you can do the same thing, you will get it. But for the case of tossing 3 coins, Uh, we will check what is the answer we got last time and what is the answer we got now, which is equal to 0.75. So it's clear that we get the same thing what we did empirically. So you have been hearing me saying empirical several times. Excuse me, empirical several times. So the word empirical refers to the case of an experiment, all right? Empirical. So we have done it empirically, but now when we have done it theoretically based on the binomial distribution, we see that we get the same solution. Now it's important to understand something as well. Why, before we end this part, there is, by the way, some of the applications of the binomial distribution that we can go through. You have different cases where the binomial distribution can be applied. These are a few examples, apart from so many examples, obviously. But I'm giving you some examples in the financial side, on the finance side. And then you will also see some of the activities that you will have on Google Classroom and an activity that you have here that you will need to go through. Okay, so you will go through this activity. We are going to discuss it later on when we meet in class. And I'm going to ask you to share your screen for this. So please do me the favor of having your work saved on your laptop so that you can share your screen with me when you have done this activity. Okay, so ensure that your work has been saved on a laptop so that when I meet you in the class, we can have a look at your solution to see what you have done. Now, before we end the binomial distribution part, let me just talk about this case of the formula. You see, you saw that f of x equal to ncx p power x into 1 minus p power n minus x. That's what we saw in the formula. Now the question is, how did we get that? Obviously, there have been people who have been working on that in the past and came up with that formula. We don't need to worry too much about that at this level. But still, we can try to understand what this formula is doing. So just remember, we were referring to the case of tossing 3 coins. So when we talk about the case of tossing 3 coins, if we want to evaluate the probability that x, let's suppose, equal to 1, okay, let's make it easier. Probability that x equal to 1, and we're talking about the case of tossing 3 coins. How can we evaluate that, and how does this apply to our example here? If we take, for example, 1 where x represents 1 head, obviously x equal to 1 represents 1 head, excuse me. So when x equal to 1 means x, we have only 1 head, you would see that if we take one possible case is that the head could be obtained on the first coin and the rest is a tail. If we are saying that x equal to 1, x equal to 1 means you have a head here, a tail here, and you have a tail. Or it could be something else. It could be that the head is here, the tail is here, and the tail is here. Or it could be that the head is here, and the tail is here, and the tail is here. Now, if we evaluate the probability of obtaining 1 head here, it's what? For one of these possible cases, it's going to be half the probability of success P times of, which is Q here, times half, which is Q here, all right? So this is what you get for one of these possible cases. So you just saw here that it is P power 1 times Q power 2 in this particular example. P power 1 times Q power 2. Q means 1 minus P. Do not forget what Q stands for. Now, then you would have to understand that this is not applied only one time, but it could be applied if the head was here and the tail was here and the tail was here. So it will still be P1 Q2 because still one head and 2 tail. And it could have been applied in a different example where you have a tail, and you have a head. So you had three times that this has been applied. Three times, three possible times where you could have obtained a head. Three possible position where you could have obtained a head. It could be for the first coin, it could have been for the second coin, it could have been for the third coin as well. So when you think about this three, what it means, when you think about this three, what it means, it's basically talking about combination case. It's talking about the combination where you are referring to one head out of three possible positions. You are looking at how many possible ways of rearranging that head here. And you have three C1 because you're talking about one head. If you were to talk about two heads, then it would have been 3C2 and 3C1 times P power 1 times Q power 2. If you think about it well now, you will see how this formula relates to what we just did here. So this formula is talking about your probability P power x, which is P power 1, Q power 2, which is n minus x, 3 minus 1, and then times NCX, that is the different positions in which the event, not the event, but the different position where the event H could have been considered. Yes. And here it is three possible ways. So if you are dealing with two heads, you will see that it is 3C2. If you are dealing with one head, it is 3C1. And if you are dealing with three heads, it is 3C3, which is obviously 1. So these are how you got this. This is how this formula can be explained in an intuitive way based on this example that we just took here. So that's all for the binomial distribution.